The law of conservation of mass tells us that no mass is gained or lost during chemical changes. And during chemical changes in particular, the identities of atoms remain intact. So atoms might form bonds or break bonds in the course of a chemical change, but a hydrogen atom is a hydrogen atom. It doesn't change into a helium atom or oxygen or something else. And this conservation of atoms that occurs in chemical reactions means that when we write chemical equations, we need to make sure that we have the same number of each type of atom on the reactant and product sides of the chemical equation. Such an equation is called balanced, and in this video we're going to talk about balancing chemical equations, and then a little bit at the end about interpreting chemical equations to get a molecular scale picture of what's happening and apply a chemical equation like a recipe to a molecular scale collection of molecules. And so we'll focus primarily on balancing a chemical equation and then talk a little bit about interpretation at the end, as I said. All right, let's get into it. So valid chemical equations are balanced. This means that we have the same numbers and types of atoms on both sides of the chemical equation, the reactant side on the left and the product side on the right. Keep in mind as well that within a chemical formula, the way we find the number of each type of atom is by looking at the subscripts, which tell us exactly this. And the only tricky thing here is that parentheses may indicate multiple copies of a group of atoms of the same type. So for example, in calcium nitrate, CaNO3,2, there are 3 oxygens within each nitrate unit, but there are 2 nitrates in the formula unit. And so we have 3 times 2 or 6 oxygen atoms in one formula unit of this compound. Just to give you an example of what a balanced chemical equation looks like, check out this reaction of 10,4-chloride with sulfuric acid, which yields 10,4-sulfate and hydrochloric acid. This equation is balanced, and to show this, we can just count the numbers of each type of atom on both sides of the equation. For example, we see one 10 atom on the left in the 10,4-chloride and one 10 atom on the right in the 10,4-sulfate. 10 is balanced. We see one sulfur atom on the left in the sulfuric acid. 2 sulfur atoms on the left in the 2 sulfuric acids. Note that that coefficient of 2 means I need to multiply this 1 sulfur by 2 in that collection of molecules on the left. So we've got 2 sulfurs on the left and 2 on the right in the 2 sulfate ions built into 10,4-sulfate. With chlorine, we've got 4 chlorines in the 10,4-chloride and 4 chlorines in the 4 HCl molecules on the product side, so chlorine is balanced. With respect to hydrogen, we have 4 hydrogens on the right in the 4 HCl's, and we have 4 hydrogens on the left in the 2 H2SO4s. So we have 2 hydrogens per H2SO4 molecule, and we've got 2 of those on the left-hand side of the equation for a total of 4. And then finally with oxygen, we have 8 oxygens on the left, 4 in each H2SO4 times 2 molecules of that type. And then we have 8 on the right, 4 oxygens in the SO4 2- anion. With 2 of those, 4 times 2 is 8. So this is a balanced chemical equation, and notice that we can check this. We'll do this again after we talk about how to balance, just by counting the numbers of each type of atom on both sides of the chemical equation. All right, very good. Now, on occasion, you'll be given an unbalanced chemical reaction or a textual description of a reaction, for example, with chemical names, where it'll be up to you to balance the chemical equation. And we do this by adjusting the stoichiometric coefficients. You can't touch the subscripts. This is not on the slide, but it's an important thing to note. If you touch the subscripts, you're changing the chemical identity of the compounds or elements involved in the chemical equation, and that's a completely different animal, right? We're way beyond balancing at that point. We're looking at a completely different chemical equation if we mess with those subscripts. So the only things we can mess with are these stoichiometric coefficients, these numbers that are out front of the species, to adjust the total count of that type of molecule or formula unit. And one thing to keep in mind here is that decimal or fractional coefficients when you're balancing are completely fine. A concern with this might be about the molecular scale or the single molecule level. How can we have a fractional number of atoms at the single molecule level? And of course, We can't, but this is still actually no big deal because we can always scale up these decimal or fractional coefficients to a set of whole number stoichiometric coefficients. And if we need to think about the molecular level in terms of whole numbers of molecules reacting, we'll need to do this, but it's always a solution to our problems. These coefficients that are decimals will have values like 1.5, 2.33, things that can be multiplied, for example, by 2 or 3 in those examples to bring them up to whole numbers. Most commonly, the way we're going to balance is just by inspection. I'll show you a bit of a more rigorous way to do this on the next slide, but that is very much not recommended because it's long-winded, it's mathematical, it's highly abstract, and it's very error-prone. You can balance by inspection using a strategy that focuses on elements that appear in only one substance on each side of the equation. That's on the slide here in blue. This is helpful since when we identify those elements that only appear in one thing on both sides of the chemical equation, we immediately know the ratio of the coefficients on those species. So let's work through an example here where we're looking at rubidium metal, Rb, reacting with rubidium nitrate, RbNO3, to make Rb2O and 1N2. And I've gone ahead and listed a stoichiometric coefficient of 1 on the N2. And when you're starting out in balancing, you can always just add a 1 to something in the chemical equation. This will get you started, and there's nothing wrong with doing this. And it's actually the best way to get started. Just throw a 1 on something and start planning things out. All right, so the first thing I'm going to look for is an element that appears only in one species on the left and one species on the right. And actually, I'm going to pause. I recommend you pause the video and identify an element of that type before I move forward. All right, let's take a look. Nitrogen only appears in N2 on the product side and rubidium nitrate on the reactant side. And so it only appears in these two species, and since I've got 2 nitrogens over here and 1 nitrogen over here, I know straight away that the coefficient on RbNO3 must be 2. This equalizes the nitrogens on both sides of the chemical equation. Now that we're here, we can repeat this process with another element if we have one, and indeed we do. You may have identified during the pause that oxygen also only appears in RbNO3 and Rb2O, and so we can also balance by inspection on oxygen, noting that now I've got, notice, 6 oxygens, 2 times 3 on the left, and only 1 on the right. So I need a coefficient of 6 out front of the Rb2O to balance this equation. Finally, the only element we have left to balance is rubidium. And now that we're here with just 1 element left, we know how many rubidium atoms we have on both sides, and we can just mess with the one remaining coefficient here to equalize the rubidiums on both sides of the chemical equation. So for example, I've got 2 times 1, or 2, on the left. On the right, I have 6 times 2, or 12. This tells me that I need 10 rubidium atoms on the left, and now rubidium is equalized on both sides of the chemical equation. It's a good idea here to check your work before you just power through. Let's make sure that we're actually balanced, applying that process we saw on the last slide to count the numbers of types, each type of atom on both sides of the chemical equation. So rubidium, 10 on the left, plus 2 here, so a total of 12 on the left. On the right, we've got 6 times 2, that's 12 equals 12. Rubidium is balanced. Oxygen, we have 6 on the left, 3 times 2, and 6 on the right, 6 times 1, or 1 times 6 as the slide says, 6 equals 6. Oxygen is balanced. Then with nitrogen, we've got 2 on the left, we've got 2 on the right, and nitrogen is balanced, and we're good to go. Balancing by inspection is what I highly recommend as far as your process for balancing. It can feel a little ad hoc and kind of random, and you might go down a path and realize, oh wait, this is too complicated, I need to back up and start again. There's absolutely nothing wrong with that. It's akin to the way we solve problems in the real world. But if you get to a really complicated example of a chemical equation, it can sometimes be helpful to just power through it systematically when balancing it. And we can do this actually using either matrix algebra or a system of equations. So with the caveat, this is not recommended. You should balance by inspection in 99% of cases. I do want to show this as an option. Okay, so how do we do this? Well, I actually want to work with this example because we already know the answer, right? From the previous slide, we know we're going to get 10, 2, and 6 for these coefficients that I've now labeled x1, x2, and x3, reminiscent of a system of equations, right? System of linear equations. And what we're going to do is essentially write these balance equations, just inserting variables, imagining we don't know what the coefficients are yet, but we know that they have to obey these three equations, one for rubidium, one for oxygen, one for nitrogen. And each of those is an equation of the form atoms of some type on the left is equal to the atoms of that type on the right, right? Just a balance equation. We can always assume one of the coefficients equal to 1, noted that in the previous process, and it's still true now, and we can always scale at the end if we don't like having 2.33 or something like this. If we don't like a decimal or fractional coefficient in the equation, we can always scale things at the end. Okay, so let's look at an example of how this goes down with the rubidium reaction that we saw previously. All right, so first I'm going to write an equation for rubidium that indicates balance. We have x1 rubidium atoms on the left plus x2. So on the left-hand side, I have x1 plus x2 rubidium atoms on the left. Don't know what those are yet, right? But we're going to solve these equations to determine what x1 and x2 are. And on the right-hand side, I've got 2 rubidiums for each Rb2O molecule, or formula unit. But with x3 of those, the total number of rubidiums is 2 times x3. So 2 times x3 must equal x1 plus x2. For nitrogen, well, the only place nitrogen shows up on the left is in RbNO3. There's one of those in RbNO3, but I have x2 RbNO3 formula units on the left, and so x2 nitrogen's on the left. And on the right, well, I've already set the coefficient equal to 1, so 1 times 2 is 2. I just have 2 nitrogens on the right-hand side. It's kind of nice. That's going to make solving this system much, much easier. All right, and then for oxygen, on the left, I have 3 oxygens per rubidium nitrate. x2 rubidium nitrates means the total is 3 times x2 oxygens on the left. And on the right, I've got 1 oxygen per Rb2O. x3 Rb2Os means I have simply x3 oxygens on the right. All right, good. And now we're just in linear algebra, solve a system of equations kind of mode, and we can, for example, substitute n for x2 immediately and come to the conclusion that x3 must be equal to 6, since 3 times 2 is equal to x3 and is also equal to 6. And now that we know x3, well, I can plug that in back up here, right? 2 times x3 is now 12. x1 plus x2 must be 12. And I already know that x2 is 2, so x1 must be equal to 10. And we've done it. We've solved the system of equations, and sure enough, these coefficients match what we found on the previous slide. 10 rubidiums, 2 rubidium nitrates, and 6 Rb2Os, along with the 1 and 2. Finally, in this video, I want to talk about applying chemical equations at the molecular or submicroscopic level. When molecules or atoms combine in chemical reactions, atoms are conserved. And so each time the reaction occurs, what we might call a reaction event or reaction occurrence takes place in accordance with the balanced chemical equation. Atoms change places, we get a new collection of molecules or atoms out of the reactant collection. And so we can work out the composition of a reaction mixture at the end of a reaction if we know the composition at the beginning and have a balanced chemical equation. This is sort of like knowing the ingredients in your pantry and having a recipe for baking cakes. From the amounts of ingredients in the pantry and the recipe, we know how many cakes we can make, right? So let me show you an example of how this works. Ethylene reacts with oxygen in a combustion process to give carbon dioxide and water, and a balanced chemical equation for this process is shown right here. Let's imagine a molecular level situation where we have 4 ethylene molecules, that's C2H4, and 7 O2 molecules, 7 oxygen molecules. What's the composition at the end of the reaction given the number of molecules in the image? Well, a fractional number of reaction events can't take place on this submicroscopic scale. So what we need to think about is applying this recipe until we run out of enough of one or the other type of molecule to actually do the reaction again. This is an idea you'll see in further studies of stoichiometry when we talk about limiting reactant. One of these reactants is going to either run out or only have a smaller number of molecules that are needed to actually do the recipe. For example, if I end up with only 2 or 1 O2 molecule at some point, those remaining O2 molecules can't do the reaction again, since 3 O2 molecules are required to do the reaction. Fractional numbers of molecules, thinking submicroscopically, right, cannot engage in a chemical reaction if there are not enough there in accordance with the coefficient. All right, so to get a better handle on what this means, what I want to do now is break up these collections of molecules into groups that can do the reaction some number of times. So for example, we've got 4 C2H4s, and I can think of that as one C2H4, another C2H4, a third, and a fourth, right? So I've got 4 C2H4 molecules, and with a coefficient of 1 in front of C2H4, that means I can do 4 reactions with these C2H4 molecules. For the oxygens, I need 3 of those to do 1 reaction. So I can break this up into 3 O2s, a collection of, say, these 3 O2s, another collection of 3 O2s, and then kind of a loner 7th O2 molecule that is not enough to do the reaction a third time. This collection of O2 molecules can only do the reaction twice, right? Once this is used up and this is used up, I only have 1 O2 left, and that can't do the reaction at the end. And so only 2 reaction events can take place given this collection of molecules, right? I don't have enough oxygen to run the reaction 4 times, even though I have enough ethylenes to do the reaction 4 times. So what will actually happen? Well, 2 reaction events will happen. 2 of the C2H4s will be used up, and 6 of the oxygens will used up. We'll get 4 CO2s, right? We run the reaction twice, so 2 times 2 is 4, and 4 waters, since 2 times 2 reaction events again is 4 H2Os. And what's left behind? Well, we only ran the reaction twice, so there are 2 C2H4 leftovers left behind, and then there's that 1 straggler O2 molecule left behind. So notice that we're essentially taking stock of our pantry, if we like, over here, and then applying the recipe however many times we can until we run out of enough of an ingredient to run the reaction again. This allows us to fully specify the composition of the reaction mixture at the end, and this includes both products and leftover reactants at this molecular scale. When you talk about limiting reactant in a future course, you'll see that on the macroscopic scale, reactions can effectively go to completion, since these sort of straggler molecules, in the case of a limiting reactant situation, end up not mattering, or we have enough of them that they're macroscopically measurable, some number of grams that we can measure, express in normal notation, all that good stuff. A couple of lingering questions to end this video. How do we make use of balanced chemical equations to plan and carry out chemical reactions? This is the field of what we call stoichiometry, and it's a big focus of study in introductory chemistry courses. Then another question, which is a little bit bigger and a little bit fuzzier, is how do we determine experimentally the chemical formulas of reactants and products and the number ratios in which they combine, right? Balancing chemical equations, if we go back here, hinges on knowing these chemical formulas. How do we learn those in the first place? How do we know the chemical formula of a compound? Really, it's a fundamental question. It's one that you'll start to explore in your introductory chemistry courses. And if you go on to organic chemistry, you'll learn a lot more about how we can use spectroscopic experiments in particular to get an idea of the composition and more detailed information about the structure of various compounds.